Dear students, welcome to the 6th sem of BSc course. Myself is Srimati Sharda Irani, Associate Professor in Chemistry, GC College, Ankola. And this time I am going to take paper 1 inorganic section and paper 2 physical section. Under paper 1, the first chapter is coordination chemistry part 2, second chapter bioinorganic chemistry, and the third chapter is non-aqueous solvents. Under the first chapter, that is coordination chemistry part 2, there are certain theories which explains the nature of bond or the type or the way of bond formation in coordinate compounds. So in the last sem, that is in the 5th sem, you have studied coordination chemistry part 1, where you have learnt the basic points and the nomenclature of coordinate compounds. And you have seen usually the transition elements, means which are having partially filled d orbitals, they prefer to form coordinate compounds or complexes. Now in this time or in this sem, the first chapter coordination chemistry part 2, under that, see the first part or the first theory is valence bond theory. So the valence bond means what? It is the bond formed by sharing of electrons along with the overlapping of orbitals. And the valence bond theory, it is proposed by Linus Pauling, and according to him, during the coordinate bond formation, the orbitals which involve in overlapping or bond formation, if they are hybrid orbitals, then the resulting bonds are quite strong. That means instead of atomic orbitals, if the hybrid orbitals are involved in bond formation, then the resulting bonds are quite strong bonds. Okay, now we'll go through the valence bond theory. See the main points of valence bond theory, which explains during the complex formation as below. Say during the complex formation, first point, say every metal ion keeps ready certain number of atomic orbitals. Says the certain number means which is equal to the coordination number of the metal ion. Okay, so it keeps so many number of atomic orbitals empty. Second point, empty atomic orbitals undergo hybridization. Empty atomic orbitals of metal ion undergo hybridization. The third point, ligand must have at least one filled sigma orbital. And the fourth point is empty hybrid orbitals of metal ion overlap with filled sigma orbital of ligand during bond formation. Okay. And the fifth point, based on the field strength of approaching ligand, the unpaired electrons which are present in the d orbitals of the metal ion may force to pair up against Hund's rule. Okay, so if n d orbitals, that means outer d orbitals, are utilized in hybridization, then the resulting complexes are said to be outer orbital or high spin or spin free complexes. Similarly, n-1d orbitals, n-1d orbitals are used in hybridization, and they are said to be inner orbital complexes or low spin complexes or spin paired complexes. So now we'll discuss by taking certain examples according to valence bond theory. Okay, so they have mentioned certain examples for your studies. So we'll take one by one. Now the first example is being K4FeCN6 is the molecule. Example 1, K4FeCN6 minus 4, or it is FeCN6 minus 4 ion. Okay, So sometimes they may ask like this, or they may ask the complex ion. Okay, so now in the complex ion, that is FeCN6. So in the last SEM, you are well familiar. So in this complex ion, the central metal ion, say the central metal ion is Fe. Okay, and Fe is in +2 state because here it is -4. Each cyanide is minus. They are 6 in numbers, -6, and Fe must be in +2 states. So now its electronic configuration, that means electronic configuration of this Fe is, say, the Ar core and 3d6 4s 0 4p 0, because iron Fe is atomic number 26. Its atomic number is 26, and electronic configuration is argon 3d6 4s2 4p 0. Okay, now say Fe is here 0 and it is having 3d6 4s2, but in the complex ion Fe is in +2 state. That means this Fe has lost 2 electrons, thereby these 2 electrons are vanished or lost, and therefore the number of electrons in Fe2 is 4s0 3d6. Okay, so now say in Fe2, see the outer electronic configuration. Just we'll write outer electronic configuration is 3d6 4s0 4p0. So we'll show the distribution of electrons in the d orbitals as well as s orbital and p orbital of metal ion. Okay, there is no electrons. Here also there is no electrons. And d orbital, it is a bunch of 5 d orbitals. They are 6 in numbers. So 1 electron, 2 electron, 3 electron, 4 electron, 5 electron, and 6 electron. Okay. So now say the Fe is forming a bond with ligand, and here cyanide is the ligand. Okay, they are 6 in numbers. When the 6 cyanide ions approach the central metal ion, so there will be a formation of a bond between Fe and 6 ligands. Now cyanide is being a strong field ligand. When 6 such ligands approach the central metal ion, then the electrons, it is a strong field ligand, and when the ligand field is approaching the metal ion, okay, then these electrons are forced to pair up. Therefore, the electronic configuration of Fe in, say, complex, in the complex is, see here, the electrons are forced to pair up. Say these are 6 in numbers, so 1 2 3 4 5 6, and now they remain empty, so 4s and 4p. So now two of the 3d orbitals, this is the 3d orbitals, two of them are made empty. Okay, now they are 6 in number, say empty atomic orbitals. This central metal ion keeps ready, according to first point, the central metal ion keeps ready certain number of atomic orbitals empty. Here 6 atomic orbitals are made empty because the coordination number of Fe is 6. Fe is 6. Therefore 6 empty orbitals are kept ready and they undergo hybridization. So now the type of hybridization is D2sp3. Hybridization takes place. Okay. So now these hybrid orbitals, now they overlap with the 6 cyanide ligands or cyanide ions which act as the ligands. Okay, so now each ligand, each cyanide, say, donates 2 electrons because they are monodentate ligands, and those ligands are placed or occupy these orbitals. So now the cyanide, the filled orbital of cyanide overlaps with the empty hybrid orbitals of metal ion, thereby forming a coordinate bond between 6 cyanide and Fe metal ion. So now the hybridization is a D2sp3 hybridization. Hence the resulting structure is octahedral. Octahedral. So now one can write the structure of complex. Okay, one is above the plane, another one is below the plane. So this will be the structure. So they are in one plane. Okay. So now there is no unpaired electrons. Hence it is diamagnetic in nature. So diamagnetic. Okay. So there is no unpaired electron. Therefore they are said to be all the spins means electrons are paired up. Therefore it is said to be spin paired complexes. Okay. Spin paired complexes. And at the same time. Okay. So the geometry is octahedral. There is no unpaired electrons, hence it is diamagnetic. All electrons are paired, therefore spin paired electrons. Now outer d orbitals are used because of the strong field ligands. The unpaired electrons are when the ligand field approaches the metal ion, these electrons are forced to pair up. So thereby the inner d orbitals are kept empty or made empty, and thereby this complex is said to be inner orbital complex. Inner orbital complex. Okay. So now according to valence bond theory, so one can explain say the structure or the formation of bond in case of either this molecule or by taking this ion. Both are same. So outer ionizing sphere is not shown here. Therefore it is a complex ion. But in the examination they may ask like this, or they may ask even directly in the ion to the ion itself. That means to explain the valence bond theory with respect to this ion. Then say you have to explain the central metal ion is iron, and during the complex formation iron loses 2 electrons to attain stable atomic state or oxidation state, stable oxidation state. And now the outer electronic configuration is 3d6 4s0 4p0 because iron is in ground state. It is 0, atomic number is 26, electron configuration is argon core 3d6 4s2 4p0. So during the complex formation where iron loses 2 electrons to attain stable oxidation state, so these 2 electrons are lost. These 2 electrons are lost. Therefore, the outer electronic configuration or the electronic configuration of Fe2 plus is 3d6 4s0 4p0. So now Fe2 outer, same thing I am writing here once again. Say Fe2 outer electronic configuration, just I have taken 3d6 and 4s0 4p0. So I have shown by picture, say 3d6 4s0 4p0. So during the complex formation, when the cyanide ion 6 cyanide approaches the metal ion, then what happens? Due to the strong field, so it affects or it forces unpaired electrons of metal ion to force, that means forced to pair up. So thereby the 6d electrons are paired like this, or they are forced or placed like this, thereby making two 3d orbitals empty, and already first s is empty and 3p are empty. So the 6 ligands are approaching, 6 atomic orbitals are made empty, and those according to second point, those empty atomic orbitals undergo hybridization, and the type of hybridization is T2sp3 hybridization. So which gives octahedral structure or geometry to the molecule. So now after bond formation with 6 ligands, so there is no unpaired electrons, hence it is said to be diamagnetic. All electrons, especially in d orbital, they are paired up, therefore spin paired complexes. And inner d orbitals are made empty, hence it is said to be inner orbital complexes. Okay, this is the explanation according to valence bond theory with respect to this complex ion. Okay, we'll discuss the next examples in the next class. Okay, thank you.